Thank you. So I'll do a short presentation of an instrument we are developing for the next NASA Rover mission. And the instrument is being developed at FFI here in Norway, but in addition to the team in Norway, that's the instrument team, we also have some collaborators. I'm principal investigator for this instrument, and I have a deputy principal investigator at UCLA, and people at the University of Dresden, different co-Is that's in the science team. Applied Physics Laboratory, Goddard Space Flight Center, University of Toronto, and so on. And two Norwegian, one Jack Holler at the Norwegian Polar Institute and Hans Amundsen at Vestfold Geophysical. So there's a lot of things about Mars these days in the news. And I won't tell you a lot of things about Mars, just point out the main points that is connected to our radar measurement. A special thing about Mars is that it's very cold and very dry place and very low pressure, meaning that all the water evaporates out or sublimates. It goes directly from ice to vapor. So there's no liquid water on Mars. There's ice on the south and north pole, but in theory there's no ice in the equator. But at ancient times there has been water, and these are a couple of illustrations showing that. You see a network of flows here that's interpreted as rivers. You also have these shaped lenses here where there's a flow going upwards. And this is an image taken by, it says Cornell, so this has to be the Mir rovers. And it shows sedimentary layering. This sedimentary layering can either be wind-driven sediments or water sediments. But Curiosity has proven now, without doubt, that this, based on the mineralogy of the surface, that it's water-based, these sediments. So at one time, there was a lot of water on the planet. And this is the way NASA explores Mars. And in the beginning, they had the slogan, follow the water, because water is central to all life as we know it. And the only life we know is on Earth. Water is dipolar, it's polar, so it dissolves ions very well and can transport them very easily. So water is point one. So they put up these two Mir exploration rovers to study the water. And they found evidence of water. The next step was to explore habitability, meaning if there's enough surroundings, the energy, the right atoms and so on to make it habitable for life. And then they shipped up Curiosity or MSL. Mars Science Laboratory, that's currently roving Mars. The next step after these two is Seek Signs of Life. It's over here. And it's two rovers going up now. The first one is ExoMars. That's a European Space Agency rover. And we at FFI, there's a ground-penetrating radar on this. It's slightly different that's on the Mars 2020. And we made the prototype for this at FFI. And I'm a co-principal investigator for this instrument here. In 2020, NASA is planning to launch a new science rover, Mars 2020, and both of these two are to look for life on Mars. So this is the Mars 2020 rover, and there's 7 instruments was selected for flight. We were actually first, the RIMFAX, we're located here. This is the antenna, and we have an electronic radar electronics up here. In the beginning, we were only selected for phase A study because they were not sure that they could fit the antenna on the rover. But now we're selected for flight like the other instruments. There are two instruments that's not part of the science package, but that are funded by the Human Mission Directorate at NASA. It's the MEDA, it's an advanced weather station. And you have MOXIE. MOXIE is an instrument that's supposed to produce oxygen from the carbon dioxide on Mars. And this is turning out to be a problem because it uses a lot of power. It actually consumes all the power on the whole rover if they want to run it. The other instruments are, it's a Mastcam-C, and that's the camera that takes all the nice images. And is the same team that's on Curiosity, and the new thing is that it has a zoom capability. It can zoom in. Curiosity, it has only 2 focal lengths. Then you have SuperCam. SuperCam is an upgraded version of the ChemCam that's currently on Curiosity. It has a laser, so it can evaporate rocks and look at the spectral signature of these rocks to remotely identify minerals. And then there's 2 instruments developed by a Jet Propulsion Lab. It's Sherlock, and that's also, it's a Raman Libs. It's also a laser instrument, but with much higher resolution than the SuperCam. And then you go to Pixel, which is an X-ray diffractometer. So all the instruments here are remote sensing instruments using electromagnetic waves in one way or another. So these 7 instruments were selected in 2014 out of, I think it was 58 proposals for this rover. And the one thing I learned here is a good thing to have been in space before, because all of these teams have been in space before. So we are the only new team coming in, and the way to get in is to have a new instrument that's not been in space before. Then you have a chance to get in. So what's a ground-penetrating radar? It's a radar transmits electromagnetic waves. So we have an antenna transmit electromagnetic waves that propagates down into the subsurface and reflects back when you hit interfaces. So this is a profile taken on Svalbard where you have a sedimentary layer on top, and then you have ice here. And this is the moraine. So you can study the subsurface of the planet. And so far on Mars, the deepest they've been in the subsurface is this much. And Mars is covered with dust. There's a lot of dust on Mars. So, excuse me, the rover may traverse very interesting places, and they don't know about it. So this will be a good opportunity to have finally an image of the subsurface of Mars. A thing that's working better on Mars than on Earth is that it's dry. There's no water. And on Earth, the water dissolves the salts, making it conductive. So on Earth, you don't see that deep in the ground. But on Mars, you have no conductivity. So you can see deeper. That's the reason why radar is a good thing on Mars. So the scientific objectives for this instrument is to image the subsurface structure and provide information of subsurface composition. So we will provide a window into the geological and environmental history of the planet, and more particular, where the planet is going. What kind of geology is the rover traversing? Another very interesting thing is to get information about past surface exposure history of sedimentary rocks. Because the organic materials that may have been there are being destroyed if they're at the surface due to radiation. Cosmic radiation is breaking down the molecular structure, and they are lost. So on the ExoMars, they have a drill that can drill 1.5 meters down to take up core samples and analyze the samples at 1.5 meter depth, because then the radiation is much less than closer to the surface. Mars 2020 does not have a drill. NASA says it's too complicated to drill on Mars. They cannot do it. ESA can do it with an Italian drill. So this is maybe we could help with this. And these things are the Mars 2020 things. In addition, this is ancient Mars, meaning that if there were life on Mars, that's 3.5 billion years ago. But RIMFAX can also study modern Mars, meaning what's the climatic condition on Mars today. So we could see buried layers of ice, liquid water, or brines, as they have discovered now. The brines, if you put brine, it doesn't evaporate so easily as with water. And so it may have a longer life down in the subsurface. So there may be brine on Mars. So ground ice, this is a very recent study published in August 2015. And you can see this, you have these terraced craters. So there's a layer here with different properties than deeper and elsewhere. And a study showed that this may be ice. And the interesting thing with this is that these craters are close to the equator. So there may be ground ice close to the equator. The one presenting this paper, they have no idea how the ice can stay there, because it shouldn't be there. But this is an interesting thing that we can study with the RIMFAX radar. Just a simple block diagram. We have the electronic box, we have an antenna, and the RIMFAX speaks with the Rover compute element, serial data interface, and we have a 28-volt power. So it's a fairly simple instrument. And it's located, these are fairly old images. And the reason is that all these illustrations, that's ITAR, so they need to be released through NASA HQ. And we are located in one of the towers with the electronics. And the antenna is located on the back. This is an old version of the antenna. And the red here is the RTG, the radiothermal generator. For those who saw the Martian, it was the stuff he was digging up and putting in the back seat. And this is producing heat, and this heat is converted into electricity and charging the batteries. This is in temperature-controlled zone. So we have to test the electronics from -55 to +70. This is outside. And this, we need to test this antenna from -135 to +110. And the reason this large span is it's very cold on Mars, and it's very hot close to this RTG. So we have a temperature gradient over the antenna. This is the development timeline. We were selected here, 2014. In January 2015, we had an accommodation review. This was a review to show that we could actually put the instrument on the rover. And we had problems with this, and all the other instruments had problems with this, because this was what they do, NASA. They take the Curiosity rover, and they strip it with the instrument, and they try to push a new instrument inside. So in the beginning, they were supposed to keep everything, but they realized they couldn't put the instrument in, so they start to reorganize everything. So there's, I think, the current version of the rover we are working on now is the version 15, but I think they are up to 18 now. The next review we just had 2 weeks ago, we had a preliminary design review. Here we had to prove to NASA that we could actually, that we had plans to build the instrument and that we could do it. Then in 2016, we will have the critical design review. This is a gate window into building the flight model. So in the NASA system, this brings in the big money. For each review, you get more and more money from NASA, if you're a NASA instrument. 2017, we need to ship an engineering model that will be used in the Rover testbed at Jet Propulsion Lab. 2018, July, we need to deliver the flight model. That's 2 years before launch. So they have 2 years to integrate the instruments on the Rover. And it will launch in, not in March 2020, it will launch in August 2020. And it takes 7 months, so it will land in February 2021. And the mission is 1.5 Mars year. And that's 3 Earth years. We are currently, we have made a prototype at FF5 for the radar. And we are currently doing design. We need to simulate the temperature in the box. And the radar consists of these 3 PCB layers. This is a prototype, the last prototype of the antenna. If you see all these strange cutouts, that's because we get the NTE, not to exceed volume. So we get a very strange volume that we need to have the antenna inside. And this cutoff came very late, and that's because they need some borescope to inspect after installing the RTG. The RTG is installed at Kennedy Flight Center just before launch, and they need to inspect the bolts and so on. Currently, we are doing thermal analysis, mechanical stress analysis of the antenna. It will have some Gs during launch and descent. And we are also putting the antenna on the rover and simulating the electrical performance of the antenna. The rover, we are looking into, we're trying to make an image. But the dynamic of the image is very large, meaning the smaller signal to the bigger signal is much larger than what we can capture in the receiver of the radar. So we need to split this in 2. We split this in 2 modes, so we have one window looking shallow and one looking deeper. So for each 10 centimeter, we collect 2 images as the rover goes. So every 10 centimeter, we take 2 measurements. These are typical what we hope to get. These are measurements. We get a chunk of data every day, and we can reveal a sedimentary structure. This is a radar prototype we took to Svalbard in April this year to do a test. This is the V13 antenna, because we got a change after that. And this is a subsurface profile of a glacier on Svalbard. So, what we hope this will bring a new dimension to Mars rover science. Thank you.
Okay, now some reactions from our panel.
Thank you. This was extremely fascinating. I have a more overarching question, if I may, and that is, why is this important? I mean, we hear about Mars all the time, all the resources put into it. What sort of implications would proving life on Mars have for humanity, for you and me?
Well, that's a fairly big question. So I think so far, it's only been discovered life on Earth. So if you can discover life on another planet, you know we're not alone. This may have happened elsewhere. And I think if we find life on 2 planets in the same solar system, that's extreme. Think of all the planets, all the solar systems. So then it must be lots of life out there.
So what's like the dream scenario of the results you get back? What would be like the best kind of results?
Yeah, the best results we could hope for is to find water. Water or ice close to the equator. That would be something completely new, I would say. Because no models that's being developed on Mars predict water or ice close to the equator. If you go to the north, you find ground ice. And to the south, we find ground ice, no doubt about it. But closer to the equator, there's nothing. That would be the big story.
How deep can you actually see? Do you know that?
No. But I can give an estimate. On glaciers on Earth, you can see a kilometer down. You can see 3 kilometers. But if you take it out in the field here, you maybe see 1 or 2 meters. But on Mars, my best guess, we could maybe see 20, 30. If we're lucky, we could see 100 meters and maybe 200 meters. I don't know. It all depends on the ground conditions, where we land. If there's brine in the subsurface, we will have problems. But if the ground is dry, we will see very deep.
But the water is the problem, but ice is
Ice
nice?
Ice is no problem. And it's the ice has a crystal structure, so all the water molecules is not polar anymore. They're locked in a crystal system. But if it's water, you have these polar molecules that dissolve salt in the ground and make it conductive.
Okay.